Okay, so as you know, this topic is called other graphs. So what we're going to be doing throughout this topic is introducing some new graph shapes that you haven't seen before. But what we want to be able to do is combine those new shapes together with the things that we know about transformations of graphs that we've already learnt through the parabola in particular, and we extended that into the cubic and the quartic. So when we talk about transformations, I mean dilations, reflections and translations. So we're starting to get a sense of what parts of an equation affect those different transformations, okay? And what we want to try and do today is to generalize those understandings that we've gradually built up through the looking at the graphs of the parabola, of the cubic and the quartic, okay? And so we want to now generalize those so that throughout the rest of this topic, as we introduce a new graph shape, we can then think, okay, I know what I would need to do to that equation if what I wanted to do was translate that graph up by 2, or translate that graph to the left by 5. Or reflect that graph. Okay, I know what I then need to do. If I know the basic equation, I know what I then need to change in that equation in order to affect that transformation. So we want to really start to take a step back from looking at specific functions and think more generally about this, so to generalize the understandings that we already have. So I'm going to do that looking at each individual transformation and some of the graphs that we already know, okay? And then we want to think about, we want to see that what's happening is the same for every graph, and therefore we could generalize that to, okay, if I have a different graph and I stick a +2 on the end of it, what is that going to do to that graph? Okay. And to be honest, it's really important that your function notation is really solid for you to start to fully understand what's happening algebraically here with some of these. So we reviewed function notation in the previous video, and we've looked at that in 2 separate sections earlier on this year as well. We started it right back in term 1 with the linear functions, and then we also looked at some function notation with the polynomials, so p of x and f of x, etc. Okay, so let's start. So we're going to take 4 familiar graph shapes. So linear graph, parabola, so quadratic graph, cubic and quartic. Okay, so those 4 basic and the most basic versions of those: y equals x squared, y equals x cubed, and y equals x to the power of 4. And think about what happens to those graphs when we do the same thing to each of them, and see that the same thing happens, and so we can generalize that to any other graph. I'll then jump over to a graphing package and just have a look at that once we've put together all the separate transformations. Okay, so 4 familiar functions and their graphs are shown below. For each of the functions, write down the rule represented by f of x plus 2 and sketch the graph of y equals f of x plus 2 on the same axis as the graph of y equals f of x. Okay, so if in the top right box here, f of x is equal to x, okay? So therefore, if we have f of x plus 2, well, if f of x is x, then f of x plus 2 is x plus 2, okay? So that is x. And so we're being asked to therefore sketch the graph of y equals x plus 2, which is what part 2 asks us to do. So y equals x plus 2, so we know that's a linear graph, gradient of 1, y-intercept at 2, okay? So y-intercept at 2, gradient of 1, it's going to go through all of these points. And that is our graph. So that is the graph of y equals f of x plus 2. Okay, in the top right box, our original function here is f of x equals x squared. So the first thing we want to do is write down the rule represented by f of x plus 2. So once again, we know this time that f of x is x squared. So we replace f of x with x squared, and f of x plus 2 is therefore x squared plus 2. Okay, you're going to take your original function and add 2 onto it. And we know if we're going to sketch that graph, so that's the graph of a parabola, and we know that this plus 2 translates that graph up by 2. So the turning point will come up here to 2, this point at 1, 1 will come to 1, 3, negative 1, negative 1, 3. This point at 2, 4 will go up to 2, 6, negative 2, 6. This point at 3, 9 will go off the chart to 3, 11, okay? And so we can draw in our graph of y equals f of x plus 2. So the original function with 2 added onto it is going to be that black graph. Okay, let's think about the cubic. So if f of x is equal to x cubed, if I want to know what f of x plus 2 is, well, that's going to be x cubed plus 2. Okay, and we know from sketching cubics in our previous topic that that's this basic cubic shape with the point of inflection translated up by 2, and so the point of inflection goes up to be at 2. Okay, and this point will also go up by 2, and this point will also go up by 2, and this point will go up by 2, and this point will go up by 2. And we have our cubic shape. Up by 2. Okay, and then if f of x is x to the power of 4, f of x plus 2 is going to be x to the 4 plus 2. So we want to sketch the graph of y equals x to the power of 4 plus 2. So we know that's a quartic graph with its turning point at 0, 2. Okay, so thinking about, turning point form 0, 0 and 2. So turning point is at 0, 2. And in fact, again, it's the graph translated up by 2. So again, we can sort of move each point up by 2. Okay, and that's our graph of y equals x to the power of 4 plus 2. Okay, so what we kind of see is, if we take our basic shape and all we do to that equation is we add 2 onto the end of it, we know that that translates the graph up by 2. So if we generalize that, the graph of y equals f of x plus 2 is simply the graph of y equals f of x after a translation up by 2. Okay, and so we can see that. I'm just going to flip over to a graphing package. Okay, so here's a graph that you don't know about. Okay, you're not meant to know about it. I've just drawn a function type that you don't know anything about. Okay, but we can see the picture of it. So if we think about this as being f of x, now my CAS actually knows this as f1 of x. Okay, function 1 of x. So if I were to sketch on the same axis the graph of f1 of x plus 2, hopefully, given what we've just looked at, we should be able to predict that that's going to be the exact same graph as I can see here, translated up by 2. Great. So every single y coordinate's been added, 2 added onto it, and it's all just gone up by 2. So let's think about if I were to instead sketch the graph of f of x minus 1. What are you going to expect to see when I press enter here? Okay, and hopefully your suggestion is it should be f1 of x, which is the blue graph, translated down by 1. There we go. Again, if you were to change it to f1 of x, sorry, if you were to change it to f1 of x, minus 5, would be the graph translated down by 5. Okay, so as long as you know the basic shape, if you then add or subtract a number onto the end of that equation, all you're going to do is take that original shape and move it up or down. Okay, all right, I'll just delete that red graph for now. We'll come back over here once we've introduced our next transformation. Okay, so let's go back. So again, the same 4 familiar functions. For each of the functions, we want to write down the rule that's represented by f of x minus 1. Okay, so this is again where your function notation is important. And once we've written down the rule for f of x minus 1, we then want to sketch the graph of y equals that on the same axis. Okay, so if my original function is x, f of x minus 1 means we replace all the x's with x minus 1's. Okay, so our equation is going to be x minus 1. Okay, so that's a straight line graph with a linear graph with a gradient of 1 and a y-intercept at negative 1. Okay, so when it's a linear graph, because it's such a simple function, it can be a bit harder to differentiate the separate transformations. So in fact, this looks the same as translating the graph down by 1, and it is in this case. Okay, but let's have a look at what happens with the parabola, and then let's be clear about the fact that actually it's the same thing happening with the line. So this is y equals x minus 1. Okay, so with the parabola, again, f of x minus 1 means replace all the x's in f of x with x minus 1's. So it's going to become x minus 1 all squared. Okay, now we know how to sketch parabolas. We know our turning point form. We know the turning point is now going to be at 1, 0, because k is 0 in this situation. Okay, so the turning point's at 1, 0. And actually what we've seen happen is the whole graph translate to the right by 1. So we move each point to the right by 1, and we get our graph of y equals, so this is y equals x minus 1 all squared, which is f of x minus 1. So the graph has actually gone to the right by 1. And actually, if we think about the linear graph, it's also true that this graph, while it looks like it's gone down by 1, which it has, it's also gone to the right by 1. That they are they are the same transformation for this particular graph type. Okay, the cubic, f of x minus 1. So replacing all the x's in f of x with x minus 1's. So that gives us x minus 1 all cubed. And again, we know that that's the cubic graph translated to the right by 1. So we take each of our points and we translate them to the right by 1. And that is y equals x minus 1 all cubed, which is f of x minus 1. Okay. And again, the quartic taking, replacing x with x minus 1. Okay, so within the quartic, so still something to the power of 4, but it's now x minus 1 to the power of 4. As opposed to the previous example where we had x to the 4 and then we added or subtracted something onto the end. Okay, so being clear about the difference between these two things. Okay, doing this would move the graph, x to the 4 would move the graph down by 1. Doing this moves the graph to the right by 1. Okay, so right by 1. Turning point comes across here. Every other point moves to the right by 1. Okay, and we get our quartic shape. Sorry, it's not the best shape. I find these quite hard to draw. Okay, so this is y equals x minus 1 to the power of 4, or f of x minus 1. Okay. So we see the same thing happens no matter what the function type. If we replace the x part of the function with x minus 1, we take that graph and translate it to the right by 1. And so we can generalize that by saying that y equals f of x minus 1 is the graph of y equals f of x after translation to the right by 1. Okay. And again, we can go over here to this graphing screen. Here's our f of x. It's called f1 of x in this case. So if I have a look at f1 of x minus 1, replacing all the x's in f1 of x with x minus 1's, that should take the blue graph and translate it to the right by 1. Let's have a look. There we go. Everything moved to the right by 1. If I were to make it x minus 3, for example, think about what you would expect to see when I press enter here. So I would expect to see that this graph is translated, the blue graph is translated to the right by 3. And in fact, correct. What about if I was to make it f of x plus 2? Okay, so f of brackets x plus 2. Okay, so the adding or subtracting is inside the function. This time we would expect the graph to go to the left by 2. Okay, so adding or subtracting inside the function moves the graph left or right. Adding or subtracting outside the function moves the graph up or down. Obviously, we could then combine those two things together and perhaps move the graph both left or right and up or down. Okay, so we've taken the original graph and translated it to the right by 1 and up by 2, and we now have this red graph. Okay, so we're starting to sort of generalize the transformations. Let's go back and have a look at the next one. So we've got the same four familiar graphs. For each of the functions, we want to first of all write down the rule represented by 2 times f of x, okay? And then we're going to sketch the graph of y equals 2 times f of x on the same axes. Okay, so if f of x is x, 2 times f of x, again, f of x is x, so that would be 2 times x, okay? So again, this is about your function notation being good. So that's now a straight line with a gradient of 2 and a y-intercept still at 0. So gradient of 2 means for every 1 across, we're going to go 2 up. Okay, and so, sorry, try that again. Okay, and so there we have y equals 2 times f of x. If we have the parabola, f of x equals x squared, so 2 times f of x is 2 times x squared. Okay, and we know that that's the parabola dilated by a factor of 2 from the x-axis. So remember, that means doubling all the y-coordinates. So if the y-coordinate is 0, it's not going to move. This point 1, 1, when we double its y-coordinate, goes to 1, 2. This point 2, 4, when we double its y-coordinate, goes to 2, 8, etc. Okay, and so we have the original parabola after a dilation by 2 from the x-axis. And in fact, if we look at the linear graph, that's actually what's happened here too. We've doubled all the y-coordinates. We've dilated by a factor of 2 from the x-axis. Okay. The cubic, if f of x is x cubed, then 2 times f of x is 2 times x cubed. Okay. And we know, again, from what we know about sketching cubics, that that is the cubic graph after a dilation by 2 from the x-axis. So again, doubling the y values, so 0, 0 will stay where it is, 1, 1 will go to 1, 2, negative 1 will go to negative 1, negative 2. 2, 8 is going to go way off the chart up to 2, 16, okay, and way off the chart down here. So it's going to be a much steeper cubic. Okay, and so we have y equals 2 times f of x, doubling all the y values. Okay, obviously that's probably not the best place. Probably haven't drawn it very accurately there. Okay, and then, oh sorry, let's fix that one there. That should be x to the power of 4. Okay, we've got f of x is x to the power of 4, so the basic quartic graph. If we then want to sketch 2 times f of x, that is 2 times x to the power of 4, that is x to the power of 4 dilated by 2 from the y-axis, sorry, from the x-axis. So all the y-coordinates are doubled. So this point at 216 is now at 232. Okay, this point at negative 216 is now at negative 232. Okay, and so we've got a steeper quartic because we have dilated it from the x-axis by a factor of 2. Okay, so this applies more generally to every single function. If you have a function, f of x, then y equals 2 times f of x is that function after a dilation by a factor of 2 from the x-axis, which means that we double all the y-coordinates. Okay. So let's, before we move on to the last transformation, let's have a quick look at that over with this graph. So again, here we've got our y equals f of x. Okay, this time the CAS calls it f1 of x. So we're going to want to try and have a look at what does 2 times f1 of x look like. Okay, and we would expect to see this graph dilated by a factor of 2 from the x-axis. So indeed, we can see that all the y-coordinates have been doubled. The graph has been stretched away from the x-axis by a factor of 2. If we were to make it, if we were to make it 3 times f of x, we would see all the y-coordinates tripled, and obviously the graph's now been sort of stretched up. If we make that a bit bigger, we can see that it's been now tripled. Okay. If we were to make it, let me just undo that rescaling. If we were to make it y equals 1/2 times f of x, we would see all the y coordinates halved, and so the graph gets closer to the x-axis, it's squashed. Okay, so a number times a function is going to dilate it from the x-axis. Okay, so if we know what the basic function looks like, we should then be able to draw 5 times f of x by dilating that function by a factor of 5 from the x-axis. Okay, let's have a look at our last transformation, and we'll come back over here to have a look at that. Okay, so here we have our same 4 familiar functions. Write down the rule represented by negative f of x and sketch the graph of y equals negative f of x on the same axis. Okay, so negative f of x, if f of x is x, negative f of x is clearly negative x. So that's a straight line with a gradient of -1. So that's, and its y-intercept at 0. So that's going to go this way. Okay. And then if we have the graph of, if f of x is x squared, then negative f of x is negative x squared. And again, remember that that's not the same as negative x all squared. So negative 2 squared is negative 4. Negative 2 all squared is positive 4. Okay, remember this is about order of operations. This is negative 1 times 2 squared. Okay, the squared happens before the multiplying by negative 1. So it's negative 1 times 4. Okay, this is the same. Negative x squared means negative 1 times x squared. Okay. Alright, so we know that negative x squared is the graph of y equals x squared reflected in the x-axis. We've seen that previously. So reflecting in the x-axis, the point that was at negative 2, 4 is now at negative 2, negative 4. Positive 2, 4 is now at positive 2, negative 4. 3, 9 goes to 3, negative 9, etc. Okay, and we can draw in our parabola, which is y equals negative x squared. So y equals negative f of x. If this is f of x, this is negative f of x. Okay, so if f of x is x cubed, then negative f of x is negative x cubed. And again, that means negative 1 times x cubed. Okay. And again, we know from having sketched cubics in our previous topic that that is reflecting the cubic graph in the x-axis. So what happens to the coordinates when we reflect in the x-axis? The y coordinates are multiplied by negative 1. Okay, and so we get the reflected cubic y equals negative f of x. If f of x is x to the power of 4, then negative f of x is negative x to the power of 4. And that is this cubic graph, this quartic graph reflected in the x-axis. And so we can generalize that to every other graph type. If I now introduce a new graph shape to you, and I say, okay, sketch me negative. So if I say this is f of x, sketch me negative f of x, you would simply take that shape and reflect it in the x-axis. So generally speaking, negative f of x is the graph of f of x after reflection in the x-axis. Okay, and that means each of the y coordinates becomes negative. So again, if we were to go back over to our graph here, then if we were to have a look at sketching negative, so remember the blue graph is f1 of x. If we were to sketch negative f1 of x, we would expect to see the blue graph reflected in the x-axis. Okay. And again, we can combine that together. So if we made it negative 2 times f of x, it is reflected in the x-axis and dilated by a factor of 2 from the x-axis. Okay, so it's both upside down and stretched further away from the x-axis. And obviously we can start to combine all these things together. So we could also add in a plus 3 and translate that shape up by 3. And then we could also change it so that it's f of x plus 1 inside the bracket, so that's going to move it to the left by 1. Okay, and we can combine together all of our transformations. Once we know the basic shape of a function, we can then sketch all the variations of that by understanding our transformations. Okay, so let's now go back over here. So here's our summary. A times a function, we'll take that original function and dilate it by a factor of a from the x-axis. Negative 1 times a function, it really is, we'll take that original function and reflect it in the x-axis. F of x minus h, we'll take the original function f of x and translate it left or right. So if it was x minus a number, it would go to the right by that number. If it was x plus a number, it would go to the left by that number. And then finally, f of x plus a number, okay? If we're adding on a number, it will go up by that many units. If we're subtracting a number, the graph will be translated down by that many units. And then obviously we can combine them all together, okay? So dilations and reflections, translations to the left or right, translations up or down. Okay, we need to be able to, and this is again where your function notation needs to be good, to identify what's happening with the function. How is it different from the original function? Okay, so let's have a look at some of the sorts of examples you're going to need to do here. So the graph of y equals g of x is pictured. So I'm not going to give you the equation for g of x. That's not the point. We're not trying to come up with the equation for g. We want to use what we know about transformations to sketch the required graph. So here we want to sketch the graph of, if this is g of x that you can see here, now sketch the graph of g of x plus 3 plus 1. Okay, so we know a plus 3 inside the function here. That's going to the left by 3. And a plus 1 outside the function here is going up by 1. So we now know we need to take this red graph and translate it to the left by 3 and up by 1. I should have given you a scale here. Let me just, so if that's 3 here, let me just divide that into 3 and sort of try to continue that scale with a bit of consistency. And again, we know that that's 2 there, so let's try and split that, -1, and try and continue that scale. So I should have given you a grid. Okay, so we're going to go to the left by 3 and up by 1. So this point that's at 0, 3 is going to go to the left by 3, so that's now at -3 and up by 1, -3, 4. Okay, this point at 2, 3, we take that to the left by 3 and up by 1. That's now at -1, 3. Okay, this point at 0, 1 to the left by 3 and up by 1, that's now at -4, 1. Okay, this point here we haven't got coordinates labelled for that, but let's move that roughly across by 3 and up by 1. It's going to go sort of roughly somewhere here-ish. Okay, and again you might take another point and say, okay, well that's sort of, you know, roughly across by 3 and up by 1 somewhere over here. Okay, alright, and then hopefully we're going to draw in our shape, which is the original graph, up by 1, left by 3 and up by 1. Okay, so this is y equals g of x minus, plus 3 plus 1. Okay, alright, example 2. The graph of y equals f of x is pictured. Sketch the graph of y equals 2 times f of x plus 2. Okay, so the 2 is going to, out the front, is going to dilate by 2 from the x-axis. Okay, so that's going to double all the y coordinates. And then the plus 2 is going to translate the graph up by 2. So that's going to add 2 to all the y coordinates. So this point 1, 3, again, let's just try and get a bit of scale here. So that's 3, 4, 5, 6, 7. Now, I might not have left us enough scale here. So if we take the point 1, 3 and we dilate it by 2 from the x-axis, we can double the y coordinate and it's going to go up to 1, 6. And then we also want to move it up by 2, so it's going to end up at 1, 8, which is going to be sort of right up here. Okay. This point at -1, 0, -1, sorry, we want to move it up by 2. Sorry, we want to dilate it by 2 from the x-axis. Okay, so this has to happen first. Dilate it by 2 from the x-axis, so that's going to be stretching it away from the x-axis by a factor of 2, so doubling the y coordinate. sorry, just by 2. So doubling the y coordinate moves it down to -2, and then we're going to move up by 2. So up by 2 is going to bring us back up to 0, 0. This point, same logic, dilate from the x-axis by a factor of 2, comes down to 2, -2, and then move it up by 2. It's going to come back up here to 2, 0. Okay. You might take some other points. So this point, for example, if you dilate it by a factor of 2 from the x-axis, it won't go anywhere. And then move it up by 2, though, it's going to be up here. Okay, same with this point. The dilation won't do anything to it. Up by 2, it's going to be up here. Okay, and so we can essentially see we're not changing the shape, we're just sort of stretching it and translating it. Oops, let's try that again. Should be there, sorry. So that's going to be basically our shape. So that's the point 2, 0, 1, 8 up here, and 0, 0 down here. Okay. So it's not perfectly precise, but it's using your understanding, and any of the points that are marked, you should definitely be able to translate those. You might transform those. You might then apply transformations to some other points just to get the shape right, and then you can draw in your graph. Okay, here's a third example. I think this might be the last one. No, there's 4. The graph of y equals g of x is pictured. Sketch the graph of y equals -3 times g of x plus 2. Okay, so the negative is going to reflect in the x-axis. The 3 is going to dilate by 3 from the x-axis. Okay, so that means the reflecting in the x-axis will make all the y coordinates negative, and dilating by 3 from the x-axis will multiply all the y coordinates by 3. So we're basically going to multiply all the y coordinates by -3. So this point, for example, at -1, 1, will go to -1, -3. Okay. This point at 1, 1 will go to +1, -3. Okay. This point at 0, if we dilate and reflect, won't go anywhere. Okay, but then we also have to move up by 2. Sorry, I jumped the gun with marking those actual points on. Okay, so it's going to come, so we reflect in the x-axis, it comes to here. We then dilate by, so reflect in the x-axis, then dilate by a factor of 3 is going to take it down to -1, -3. And then we're going to move it up by 2. So in this case, that will actually bring it back to that same point there. Okay, so it's going to be there at -1, -1. This point here, same idea. Reflected in the x-axis comes down to 1, -1. Dilate it by 3 brings it down to 1, -3. Up by 2, it's going to bring it back up to here. Okay, so that's going to be at 1, 1. Sorry, I'm just going to move that point over. And then the origin, the point at the origin, dilating it is not going to move it, reflecting it won't do anything, but up by 2 will, so it's going to be up here at 0, 2. And then we can join those points up with the same shape as the original graph. And we have our graph of y equals -3 times g of x plus 2. Reflected, dilated by 3, so that's why it's thinner, and then up by 2. Right, example 4. We've got the graph of y equals f of x is pictured. Sketch the graph of y equals -4 times f of x minus 1. Okay, reflect in the x-axis, the negative out the front. So that's going to mean the graph goes this way. Okay, then we're going to dilate by 4 from the x-axis. So all the y coordinates get multiplied by 4. Okay, so it's going to be taller and thinner. Okay, and then we're going to go right by 1. So we're going to move it across by 1. Okay, right. So let's do that to each of the points to get them in the right place. Okay, so -1, 0. Reflecting in the x-axis doesn't do anything. Dilating from the x-axis doesn't do anything. We're going to move it to the right by 1, so it's going to come across here. Okay. the point at the origin. Reflecting, it won't do anything. Dilating, it won't do anything. Move it to the right by 1, it's going to come across to here. And 1, 0, reflecting and dilating won't do anything, but moving it to the right by 1, it's going to come across to sort of here. Okay, so we've got those 3 points. That's going to be the point 2, 0, that's already labelled, that's 1, 0, and this is going to be 0, 0. Okay. I might label them after I draw the graph in so it doesn't get too crowded. Okay, then let's think about these points. Okay, maybe we'll go with the positive one first because then it'll be nice and symmetric. We can just do the other one. So reflecting it in the x-axis, it's going to, the y-coordinate will now become positive 1/4. Dilating by 4 from the x-axis, the y-coordinate is going to become positive 1. And moving it to the right by 1. Okay, so at the moment we're at 1 on root 2 plus 1. And then we want to move to the right by 1, so that's going to be adding 1 onto our x-coordinate, and thinking a bit clearly about the scale here. So this sort of distance is 1, so we want to move it to the right by kind of that sort of distance again. Okay, so it's going to be roughly somewhere sort of here. Roughly somewhere sort of here. And that's going to have coordinates that are 1 on root 2 plus 1 and 1. Okay. So again, similar logic here. This point here, reflecting it in the x-axis, it's going to come up here, so it'll still have the same x-coordinate, but it'll have a y-coordinate of positive 1/4. Dilating by 4, it's going to have a y-coordinate of positive 1. Okay, so we're now at negative 1 on root 2 plus 1. Oh, sorry, negative 1 on 2, 1. And then we want to move to the right by 1, so we're going to add 1 onto that x-coordinate. We're going to move the graph to the right by 1. Okay, so that's sort of going to be somewhere roughly here. So it still should be the same graph with the same sort of symmetry and the same sort of shape, but it is upside down and it's dilated so it's taller and thinner and it's translated to the left. Okay, so again, this is the point 2, 0, this is the point 1, 0, this is the point 0, 0, that was negative 1 on root 2 plus 1, 1, and 1 on root 2 plus 1, 1. And so there is our graph. So thinking about understanding the transformations and how do I then do that to a graph. So when we translate left or right, we're adding or subtracting onto the x-coordinate. When we're translating up or down, we're adding or subtracting onto the y-coordinate. When we're dilating, we're multiplying the y-coordinate. And when we're reflecting, we're making the y-coordinate negative. Okay. All right, so there is some work for you to do playing around with transforming functions on a worksheet today.